Hello and welcome to section 6.3, where we'll learn about orthonormal bases, the Gram-Schmidt process, and QR decomposition. So our objectives are to convert a basis to an orthonormal basis. It's called the Gram-Schmidt process, and to do a QR decomposition on a matrix. First off, we want to start off with a question: why are I, J, and K such a good basis? I hope you came up with the fact that they are each orthogonal to each other. And another bonus thing is they each have length 1. Okay. So I know we overuse this word, but in this case, when we're talking about something having length 1, we say that it is normal. So since they are orthogonal, pairwise orthogonal, and they are each normal to each other, we call I, J, and K an orthonormal basis. So next up, we want to make up any non-trivial vector you want. I had my calculator randomly generate some numbers between -5 and 5 and came up with -2, 4, and 3. So let's go ahead and find the magnitude of A with our standard Euclidean inner product. Well, to do that, and your vector may be slightly different, we're going to do A inner product with A, but that's just going to be our dot product, because that's what the Euclidean inner product is. And so that'll give us -2 squared plus 4 squared plus 3 squared. That's 9, and 16 is 25, plus 4 is 29, and since that was the magnitude squared, the magnitude of vector A would be the square root of 29, so between 5 and 6. Okay. And let me show you a image of course, our IJ vectors, IJK vectors. So here they are in orange. We've got our I vector, our J vector, and our K vector in the X, Y, and Z axes respectively. And they do form a nice basis because they're each length 1 and they are each orthogonal to each other. So let's go back to our image, our paper here. What about if I change things up a little bit? What if I use vector V1 is 4/5, 3/5, 0. V2 is -3/5, 4/5, 0. And vector V3 is 0, 0, 1. Is this set S a basis for R3? I'm going to let you pause the video and answer that question. So we'll pause here. So I got the answer is yes, noting that the dimension of R3 is 3 and that we have 3 vectors. We saw in a previous section that if you have the same number of vectors as the dimension, you only need to check for linearly independent or span. And as a general rule, it's easier to check for linear independence. And if we set up this system right here, this matrix, we will find out that C1, C2, C3 have to equal 0 for that to be true. Let me show that matrix here. So that system would correspond to the matrix 4/5, 3/5, 0, -3/5, 4/5, 0, and 0, 0, 1. And we're solving that for equals to the 0 vector. And if you RREF that matrix, you will in fact get the identity matrix augmented by 0, showing that C1, C2, and C3 all have to be 0. Therefore, our vectors are linearly independent. None of them is able to be expressed as a linear combination of the other guys. So let's go look at our picture of these guys. So here was I, J, and K. Let me undo those guys, and then let me show you V1, V2, and V3. Okay. And you'll notice that they also are pretty snazzy. In fact, it looks like they also are orthogonal to each other. And maybe we want to check and see if they are also length 1. Let's go ahead and show our I, J, and K vectors on top of that. It looks like those purple vectors are all the same length as the orange vectors. And that one on the z-axis looks black because we've got an orange and purple and a blue axis all together, and it's kind of just coming out black. So let's check and see if they are in fact linearly, I'm sorry, if they are orthogonal to each other. And so let's do vector 1 inner product vector 2. And unless otherwise specified, we will use the standard Euclidean inner product. So we'll get 4/5 times negative 3/5, which is negative 12/25, plus 3/5 times 4/5, which is 12/25, plus 0, which is 0. V1 inner product V3, that's going to be easy. We get 0 plus 0 plus 0. And if we do V2 with V3, for the inner product, we'll find out that we'll get 0 plus 0 plus 0, which is 0. So they're mutually orthogonal. And if we find the magnitude of vector 1, it's going to be the square root of 4/5 squared plus 3/5 squared plus 0 squared, which is the square root of 16/25 plus 9/25, which is the square root of 25/25, which is 1. You can also find out that the magnitude of V2 is also 1. And of course, the magnitude of V3, since it's actually the same thing as the k vector, has to be magnitude of 1 as well. So these S vectors have the same special properties that the I, J, and K vectors do, in the fact that they are mutually orthogonal and they each have length 1. And when that happens, we call these vectors an orthonormal basis. Oops. Okay. So what we want to do now is take our made up A vector, just randomly chosen, and write him as a linear combination of these basis vectors. And since they're a basis, we know they can cover the entire space. So to do that, we get C1V1 plus C2V2 plus C3V3 equals A. That's going to set up the following system. Negative 2, 4, and 3 as our constants. And when we RREF this matrix to find the constants, C1, C2, and C3, we will get the identity on the left-hand side. And on the right-hand side, let's see what we get. I just did that on my calculator. Ooh, can you see that? So we get 4/5, 4 and 2/5, and 3. So 4/5, 3 down here. Let's see, 4 and 2/5 would be 22/5. Okay. All right. So that's pretty spiffy. So to make the A vector, negative 2, 4, and 3, I would use 4/5 of the vector 4/5, 3/5, 0, plus 22/5 of the vector negative 3/5, 4/5, 0, and not surprisingly, plus 3 times the vector 0, 0, 1. Okay. All right, and what we're going to do is we're going to look at this. To make this guy, we had to use these constants. Okay, but as we remember, this is, if we were to look at this guy, he was negative 2 of the I plus 4 of the J plus 3 of the K. So these are the coordinates with respect to the I, J, K basis. So these are the coordinates of this location, this vector, but with respect to the S basis. So his coordinates, his location is 4/5, 22/5, and 3. And the last thing we'll do here in this video is find the magnitude of this vector with respect to the S basis. So that's going to be the square root of 4/5 squared plus 22/5 squared plus 3 squared. And that's going to give us the square root of 16/25 plus 22 squared is 484/25, and 3 squared is 9, and 9 times 25 is 225/25, which would give me the square root of 725/25. Let's see, I think 25 will go into that. In fact, it will go in 29 times. So the magnitude of this vector with respect to the S basis is square root of 29. Hey, that's pretty cool, because it's actually the same as the magnitude of the vector with respect to the original IJK basis. So to keep these about 10 minutes, let me stop there and we'll pick up in the next video.